Now I would like to explain how you reduce a flow to a map. That map is called Poncare section. Imagine that you have your dynamical system in a state space. So here is our state space M. And within it, there is a trajectory. Now we construct a hypersurface. Let's call it P for Poincaré, whose dimension is codimension 1. What that means is that if the state space is three-dimensional, as we are visualizing it now, this is just a two-dimensional surface. If state space is 27-dimensional, this is a 26-dimensional hypersurface, which is hard for us to visualize, but no problem implementing as computation. And this surface has to be designed in such a way that it cuts the jumble of our spaghetti that fill out the state space, the orbits. It cuts them transversely. So here I've taken a periodic orbit, and you notice that this periodic orbit cuts that surface once here at point 1, then it goes around, tuk, 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 cuts it again. And then it goes around and, goes behind and cuts it again. And then it cuts it again, but in wrong direction. So Poncare section is not only that it's a hypersurface that the orbit should cut transversely, but it should cut it in the same direction every time. If it cuts in the opposite direction, as you'll see, this is not a natural thing because you're trying to describe with a Poncare section a whole neighborhood of orbits, just like yours, but slightly off from your orbit. That's a Poncare section. One thing you have to understand about Poncare section, it is not a projection. So what we mean by projection, it's not a projection onto lower dimensional state space. When you take a Poncare section, you don't lose any information about the system. All you're doing is you're changing your coordinates in such a way that one coordinate, the one that went out of, this one is one of the coordinates. That goes out of Poncare section. It's called a longitudinal coordinate, and rest at transverse. If you want to find any point on the orbit, you can just start at the section and integrate to it. So you haven't lost any information by going this way. So you can always reconstruct your trajectory, but the new coordinates are much smarter than the original ones, as you will see. So more precisely, a Poncare section is a hypersurface that can be specified implicitly by any functions. So if I set a condition that some function is 0 whenever I cross the section, I impose one condition on the system, so it reduces the dimensionality of the space on 1. That's how we get codimension 1 surface. And we have to make sure that it's transverse. So at that point, the tangent to our curve is this velocity vector. The gradient of the hypersurface, if you don't know about it, learn about it, but the gradient of the hypersurface is something of this condition, is something that's 0 in the surface itself because condition remains 0, but it's non-zero going out, and it's actually a vector which is normal to the surface. So we have some notion of a dot product in this space, not entirely obvious, but imagine it's Euclidean space or state space. Then the dot product times the W should not be 0. Then we know that we are cutting through and not being within the section. And in this way, the continuous time flow is reduced to a sequence of oriented traversals. I guarantee oriented by making sure that this is, for example, just positive or negative, that these are all crossing same sign.